Hi, my name is Adolfo Neto, and I'm a professor at the Federal University of Technology, Paraná. And today I'm going to talk about this text, Elixir and the Bean, how concurrence really works. This text was written in 2019 by Sophie DeBenedetto. She's a software engineering based in Brooklyn, and she currently works at GitHub. She's also one of the hosts of the Bean Radio podcast. And in this episode 16, the panel talks Elixir with King Wilton. I believe Bruce Tate mentioned that post. I'm not sure. So I'm going to read and learn with you. So Elixir has become famous as the Chinese concurrent programming language. And what actually makes Elixir concurrent? So to find out, we need to understand OTP and the Erlang VM. So Sophie says, I don't understand concurrency. She's coming from to Elixir from a Ruby and JavaScript background. She understood that concurrence was something I wanted in a language. However, even after a few years of programming Elixir, I didn't really understand how it operates concurrently. I had heard of the Bean and worked with OTP, but I would be hard-pressed to give more than a passing definition of either. Many career change programmers, those of us who came to coding without a CS degree, learn by getting our hands dirty. We build things. As a result, we can sometimes take for granted how something works and remain satisfied by the fact that it does work. Add to that the difficulty of and even embarrassment around asking stupid questions, and you end up with me, someone who has programmed code that runs on the bean, but can tell you what the bean is. Over the past few weeks, my curiosity about the foundation of Elixir has grown. The passing of Joe Armstrong, who died in 2019, one of the creators of Erlang, inspired me to learn more about his work, while Bruce Tate and James Edward Gray's beta release of their book, Designing Elixir Systems with OTP, now in its version 1.0, got me thinking about what OTP really means. Keep reading if you want to stop bragging about the fact that Elixir is concurrent and start understanding how it enacts that concurrency. So, what's the bean? The bean is Bogdan Erlang Abstract Machine. It is the Erlang virtual machine. So, it's a virtual machine for another language. In this post, we will refer to bean and Erlang VM interchangeably. Erlang and Elixir, and of course other languages in the Bean ecosystem. Erlang and Elixir code is compiled into bytecode, the .bin files you may have noticed in your compiled Elixir applications, by the compiler for each language. That bytecode is then executed on the Bean. The Bean and OTP. In order to talk about the Bean, we need to talk about OTP. OTP is a set of Erlang libraries, which consists of the Erlang runtime system, a number of ready-to-use components, mainly written in Erlang, and a set of design principles for Erlang programs. This is from the GitHub, the OTP project on GitHub there in the Erlang organization. In fact, in order to install and use Erlang on your machine, you will install and build an Erlang OTP distribution. OTP provides modules and behaviors that represent standard implementations of common practices like process supervision, message passing, spawning tasks, etc. For example, the OTP framework's definition of the gen server behavior is an abstraction of common uses of interactions with certain types of process. So instead of rolling your own server and reinventing the wheel with every new application, all of us Erlang and Elixir programmers can subscribe to a shared, mature, and battle-tested server interface by using the GenServer module and behavior. OTP also encompasses the Erlang Runtime System, ERTS. That means that the OTP framework includes the bin. So when we talk about the bin, we are talking about a virtual machine built into the OTP distribution. Great. The bin and parallel processing. As part of the ERTS, the bin is responsible for scheduling Erlang processes. This is where concurrency magic happens. The bin uses one OS operating system thread per core. It runs a scheduler on each of these threads. Each scheduler pulls process to run from its very own run queue. The bin is also responsible for populating these run queues with Erlang processes to execute. In order to understand just how cool this is, we need to understand Erlang's relationship to concurrency. Concurrence in the creation of Erlang. The Erlang programming language was developed by Joe Armstrong and others, Robert Verdin, Mike Williams, working out of Ericsson's computer science lab in 1986, and a few years before. Ericsson built and maintained large telephone exchanges with hundreds of thousands of users. These systems had an important requirement. They could never fail. They had to be completely fault-tolerant. As Joe dove into developing massive fault-tolerant systems, he saw that a feature of these systems was concurrency. So this is from Erlang Solutions blog, right? Yes. 2019. Initially, I wasn't really interested in concurrence as such. I was interested in how you make fault-tolerant systems. A characteristic of these systems were that they handle hundreds of thousands of telephone calls at the same time. Having recognized this characteristic, he began to conceptualize concurrence-oriented programming, a way of modeling applications that mirrors the world around us. The world is parallel. If you wish to write programs that behave as other objects behave in the real world, then these programs will have a concurrent structure. People function as independent entities that communicate by sending messages. That's how Erlang processes work. Erlang programs are made up of lots of little processes, all chattering away to each other, just like people. This is from Joe Armstrong's blog, and I believe this part of the text is also in his book, Programming Erlang. With this model in mind, Erlang was developed to be fault-tolerant and concurrent. But what does it really mean for a language to be concurrent? The history of multi-core processing in the bin. Before Intel released the Core 2 quad processor in 2007, computer chips contained one single core. A core is a part of a CPU that receives instructions and performs actions based on those instructions. In the single-core world, computers had the ability to execute processes concurrently, but not in parallel. But wait, aren't concurrent and parallel the same thing? Nope. Let's imagine we are doing something we hate, like two enormous loads of laundry. We sort our darks from our lights and head to the laundromat. This example is a little bit USA-like, but it's okay. I believe we can understand. Laundry is the worst and takes forever, so we want to try to minimize our time at the laundromat. Instead of doing each load of laundry synchronously, load the darks, add the detergent, put in the coins, press start, wait for the cycle to finish, put the laundry in the dryer, repeat with the lights load. So you first wash and dry the darks, and then you wash and dry the lights. We decide to do both loads of laundry at the same time. We load the darks in one machine, so for this you need to have two machines, two washing machines and two drying machines. And we load the darks in one machine and the lights in the other. We add the soap to one machine and then to the other. We add the coins to one machine and then to the other, and we press start on one machine and then the other. This represents a concurrent set of processes. Both the dark load of laundry and the light load of laundry are in the same state at the same time. But this happened as a result of us quickly switching back and forth between each process. This is the switch, performing a single step of the processes for the dark load and then the light load. In this concurrent one-core world, the Erlang VM ran one thread with one scheduler on the available core. The scheduler plucked Erlang processes from the single run queue and allotted a time slice to each process. If a process exceeded its time slice, the Erlang VM would pause the process, put it back on the queue, and move on to the next item on the list. This is a very important feature of Erlang process that the Erlang VM is always able to stop the process, right? In this way, the Erlang VM would execute Erlang processes concurrently by quickly switching back and forth between processes, just like we quickly switched here, the switching. We quickly switched back and forth between our loads of dark laundry and light laundry to watch the loads at roughly the same time. Okay, and now there is this image, the scheduler. For each a task goes to the scheduler, is executed, then a task goes to the end of the queue, and the queue is going to this task goes, and then this other, then the second task, and then the current task is going to the end of the queue, and that's how it works. With the advent of multi-core processors, the bin was able to utilize a symmetrical multiprocessor in Erlang. The first iteration of SMP in the Erlang VM came out with the release of OTP, Erlang OTP R release 11b in 2006. This version of the Erlang VM could run anywhere from 1 to 1024 schedulers on one thread each, sharing the same run queue and running on the same single core. Great. And with the release, so these tasks can go to different schedulers. I believe it's not here. Yes, it's going to be explained later. With the release of OTP, release 12b in 2007, the Erlang VM running on a multi-core processor became capable of claiming one thread per core on which to run a scheduler. Sorry, the Erlang VM running on a multi-core processor became capable of claiming one thread per core on which to run a scheduler. This allowed for the parallel running of Erlang processes as a set of schedulers across cores pulled from a shared run queue to execute process. So this is what happened at that time. So you had one scheduler, for instance, if you had 3 cores, you have many tasks, but these schedulers got their tasks from the same run queue. That's what I'm understanding here. So Erlang's existing, and this allowed for the parallel running of Erlang process. So parallel because each task could be running in one task here, one here, and another in scheduler 3 as a set of schedulers across cores pulled from a shared run queue to execute processes. So Erlang's existing ability to execute concurrent process allowed it to immediately adapt to running a parallel process on multi-core computers. Adapt to running parallel processes on multi-core computers. To revisit our laundry analogy, imagine that we are joined by a helpful friend who just loves doing laundry. Thank God. Also, who? They show up to handle the dark load while we wash the lights. Now we are loading each set of laundry into 2 different machines at the same time. We have achieved parallel processing. This is parallel processing. The darks here, the lights here, the 2 processors, the man and the woman. We can see an indication of this capability in action by starting an IX shell on our machines. Let me try this with my machine. I have already tried this, but you're not seeing because I have to share. Let me share my screen here. Okay, now you can see this SMP 88, DS 8810. Yes, I don't know what's the DS yet, but here is the portion of the prompt SMP44 indicates that my machine here has 4 available cores with 4 schedulers available, 1 on each core. In my case, it's 8 cores with 8 schedulers. Great. The second iteration of SMP on the Erlang VM was limited by the fact that the set of parallel schedulers running across cores is still share the same run queue. The data in the queue had to be locked to avoid contamination. This had the potential to create processing bottlenecks, where one slow-running process unlock or lock conflict arose, where one slow-running process or lock conflict arose, all of these schedulers waiting to access the run queue would be delayed. So if we had one slow-running process or a low lock conflict, there was all the schedulers had to wait to get another task from the run queue. For example, if you and your weird laundry loving friends are sharing the detergent bottle, one person's reach for the detergent will prevent the other from moving forward with the next step of the laundry load process. Here they are. But this is your laundry loving friend. Let him have the detergent, Sophie. This issue was resolved by the release of the OTP release 13b, which moved away from the common run queue and implemented dedicated run queues per thread per core. Today, the Erlang VM runs on one thread on each core. Each thread runs its own scheduler that pulls from its very own run queue. Data is not shared across queues, so there is no need to manage locking. Everyone gets their own laundry to load and their own bottle of detergent to use. Here they have each one a run queue. How does the bean manage parallel processes? The bean creates a thread per core, a scheduler per thread, and a run queue per scheduler. It's also responsible for populating all of the run queues with processes for the schedulers to execute in parallel. Okay, so the bin populates the run queues. Great. This is managed by bin's load balancer. The load balancer implements migration logic to allocate processes between run queues on the separate cores. This logic helps the load balancer take jobs away from overloaded queues, task stealing, and give them to empty or underload ones, task migration. The load balancer aims to keep the maximum number of runnable processes equal across schedulers. So the load balancer is here, it gets the tasks and assigns them to run queues. Conclusion. Taking this dive into the how of Elixir and Erlang concurrence has definitely given me an understanding of and appreciation for the tools I've been using. I hope it's done the same for you. For further reading, check out the resource below. So this is the bin on Wikipedia. This one we have already seen. There is this book, Learn Use Some Erlang for the Great Good, for Great Good, the bin. It's only that here, not much. And Erlang Solutions, and this is from Erlang Inside the Erlang VM by Kenneth Flooding. Another one from Learn Use Some Erlang from Great Good by Fred Ebera. This blog post on load balancing from the Bing book. Great. And something from, yes, Kenneth Flooding on CodeBean. No, Erlang Factor. Now it's called CodeBean, but in the past it was Erlang Factor in 2009. Okay, that's it. I hope you have learned at least a little bit from this text by Sophie DeBenedetto. I surely did learn a bit, if not a lot. So see you next video. Bye bye.